Thank you. So the title of my talk is Non-Control of 1D Parabolic PDE using Flatness and Semi-Discretization. This is joint work with my doctoral student Soham Chatterjee. So let me set up the problem. So we are interested in this boundary control 1D PDE. So you have this equation ut is theta uxx plus sigma ux plus lambda u, where u is the state, we assume it's in L2. The coefficients theta, sigma and lambda, they are piecewise C1 coefficients. So they can be discontinuous, but on a finite number of intervals, they have to be C1. Okay? We have a boundary input F acting at the end x equal to 1, at x equal to 0, you have an homogeneous boundary condition. So this is a PDE we are interested in. And first we'll try to understand a little bit about the solution of this PDE and what is the problem we want to address. The state operator of this PDE is this differential operator on the right. So AW is theta WXX plus sigma WX plus lambda W, where this operator is defined on natural domain. And it's known that A generates a strongly continuous semigroup and analytic semigroup on L2. All right. So to define solutions to this equation, what we do is we do a transformation which will take this function, input function F to the domain, okay, into the domain. So the transformation is this: you define U is W plus nu F, where W is the new state and nu is a fixed function which has these properties here, and F is the control. When you do this, the control input moves from the boundary into the domain. And when you do that, then you can write down the usual convolution formula for the solution, and that's the formula written here. Okay, and this formula is valid whenever F is C1 or piecewise C1. So you can take a derivative of F and you have this formula for the solution to the PDE. So what's the problem we are interested in? So the problem we are interested in is, given an initial state U0, which is in L2, right? We want to find an control input which transfers this PDE, okay, PDE solution from U0 to 0. Okay, that's a null control problem we are interested in. Okay. This, of course, Professor Rosier in this workshop itself has given a very comprehensive and nice introduction to the null control problem for 1D parabolic PDEs and also how flatness can be used to study it. So we are going to give a different proof wherein we are going to combine flatness with semi-discrete approximations. So we will not be applying flatness to the PDE, but instead we'll apply flatness to a semi-discrete approximation, then get a null control signal for the ODE, take the limit of that and show that that's in fact a null control signal for the PDE. That's the approach we're going to take. All right. So this is the outline of my talk. First, I will briefly recall the flatness technique for ODEs. Then I will show that the semi-discrete PDE we get from the parabolic equation is in fact flat. So using that property, we'll show how to get null control signals, how to build solutions to the null control problem. Okay, so this will involve certain showing that certain null control signals developed for the semi-discrete system converge as you let the discretization step size goes to 0. Okay, so that part we'll cover here, convergence of the null control signal. And to do this, we need to understand some properties of the semi-discrete system. So I'll introduce those, and then I'll complete the talk with an example. So let's first recall the flatness technique. So you have a control system, U dot is alpha, U comma F. U is the state of the control system and F is the input. Okay. Now, what do you mean by a flat system? Okay. You say a control system is flat if there exists an output Y. So Y is some function of U. You should have this map beta. Y is equal to beta U. Such an output of this form, such that the state U of the system and the input F can be expressed in terms of Y and its derivatives. Other words, you should have function phi such that U is phi, a function phi, okay? It can be expressed in terms of Y and its derivatives. Same thing for F. So these functions phi and psi should exist. Okay? If this is the case, then you say the system is flat and you say such an output to be flat output. Okay? So now, yeah. So in general, flat outputs may not exist, even in the case of linear ODEs. Flat outputs may not exist. And when they exist, they may not be unique. But suppose you have a flat output, then once you assign a trajectory to the flat output, suppose you say, I'm taking Y to be certain function, right? Certain function, then Through this relationship, the flat output will determine the state of the system, control system. Through this through this function, it will determine the input. And when you take this input, then the corresponding trajectory will be given by this u. Okay. In other words, the flat output determines the initial state, final state, trajectory, and the input that takes you from the initial state to the final state. So once you specify the flat output, everything is specified via these relations. Okay. Let's now see how we can do motion planning with the when you have a flat system. So you have the control system, u dot is alpha, u comma f, y is beta of u. It's flat, so u and f can be expressed as linear combinations of y and their derivatives. Okay, so this is how you do a motion planning problem. So you have an initial state, given initial state, and you have a final state ut where you want to reach it, you reach from time 0 to time capital T. That's a motion planning problem you are addressing. So what you need to find is a function yr such that, smooth function yr because we are differentiating it many times, a smooth function yr such that the initial state u0 can be obtained in this form. So if you take yr of 0 and the derivatives of yr at 0 and you put them into this formula, you get a state, that state should be u0. Similarly, you take the function yr and its derivatives at capital T and plug it into this formula, the formula here again for phi, right? Then you get a new state that should be ut. So you must find a function yr which has this property and it should be smooth. Once you do that, you can assign your flat output y to be yr, the function you have found, and then using this formula here, you compute the input f. Then this input will do the transfer. It will take you from u0 to ut. Okay, this is how you do motion planning with the via flatness. So let me quickly look at an example because we will be looking at systems of this type. These are called strict feedback systems. So we'll see an example of that type. It's a fourth order system. So when I write down this system as first order equations, scalar equations, I get u1 dot is u1 plus u2, right? So u2 dot is 3u1 plus 2u2 plus u3 and so on. Such systems are called systems in strict feedback form because u1 dot depends on u2, u2 dot depends on u3 but not u4 and so on. So if you want to extend this idea to nth order system, uk dot will depend on uk plus 1 but not beyond. Okay, these are called strict feedback forms. When you have a system in strict feedback form, then flatness is natural. You get flatness easily. So how is it? Well, I can write this first equation, u1 dot is equal to u1 plus u2 as u2 is equal to u1 dot minus u1, right? I can just take u1 the other side. Similarly, here I can keep u3 on this side and take the remaining terms on the other side, get this equation and so on. So now if you take the flat output to be u1, then what do you see? You say u2 can be written as in terms of u1 dot and u1. So now u2 is in terms of u1 and its derivatives. I can use that in this expression and then get u3 in terms of u1 and its derivatives and so on. All right. So if I do this, I can clearly see that u1 is a flat output for this system. Okay. So now let's look at the semi-discrete PDE we are going to consider, and then we'll very easily see that the semi-discrete PDE is in fact flat, so that we can do flatness-based design for it. So for the sake of explanation, I'm going to consider this simpler PDE, right? The only coefficient is, especially varying coefficient is C, which is piecewise differentiable. But whatever I'm going to present applies to the PDE that I showed in the first slide, okay, the more general version. So I first do a semi-discretization via finite difference, okay? I do finite difference, you'll see why it's convenient in this setup. So I take the usual technique, I discretize that into n nodes, right? And Vn1 will be the value of the solution at the first node, Vn2 will be value of the solution of the PDE at the second node and so on. And I discretize it this way. And then finite difference approximation, I can approximate the second derivative using Taylor series. I get this expression, approximately this is what I have. So now uxx at the jth node is going to be ut at the jth node minus c u at the jth node, right? So I can have an equation now, and that's the equation I have. Okay, I've replaced basically the functions with their values at the nodes. All right, now I remove the approximation sign, then I get a semi-discrete approximation. Okay, so this expression Vn dot, Vnj dot, this expression is exactly what I have here. And of course, I have equations which are close to the boundary, they're slightly different. So this is my semi-discrete approximation for the parabolic PDE I'm considering. And you can immediately see that this is in the strict feedback form. Yet Vn1 dot depends on Vn2, not on Vn3 or only Vn2. And similarly, Vnj dot at the max depends on Vnj plus 1. Okay, so for using the same logic that I presented, we can see it's flat. Okay, so I'll mention this again in a moment. So we have this setup where we write Vn dot as An Vn, Bn Vn, Fn. Okay, this is a semi-discrete system we are going to do flatness design for. Okay. So the alternate form, like I took these equations, I can rewrite them in this form where I'm basically taking the Vn2 and Vnj plus 1 to the other side. Then like I explained to you earlier, you get a strict feedback form. So now y is equal to Vn1 is a flat output for the system. Okay, this is a flat output. So if I specify Vn1, I can basically get all the remaining values of the function at the other nodes, and I can also get Fn. So I get this expression where I can write each entry of the vector of the semi-discrete ODE as a linear combination of y and its derivatives, and same thing for the function Fn. Okay, and this is a flat output. Now, as I explained earlier, we can do motion planning with this. So what we want to do is we want to do null control for this system using one at the ODE level, and then try to take the limit and show it works at the PDE level. So what I'm going to do now is basically I'll tell you what the procedure is, what is the algorithm. We'll say how do we do null control, okay, using the ODEs, and then I will show subsequently that the algorithm that I'm presenting in fact works. Okay, first I want to present just the algorithm, so it's something that we can follow to use it. Okay, so we have this PDE, ut is equal to uxx plus cu, and we have this input f. So the question is, find the control input f, which transfers the initial state u0 in L2 to the origin of the finite time interval 0, t. This is a null control problem we are looking at. And we are seeing the semi-discrete ODE for this system is Vn dot is An Vn plus Bn Fn. This is a notation I'm going to use. The state operator for the semi-discrete ODE is An, the control operator is Bn. Now, because I want to transfer u0, for the semi-discrete system, I'm going to take the initial state to be Rn u0, where Rn is a operator which simply discretizes. Okay, so if you have a continuous function, you just Rn z is nothing but evaluation of that at the n nodes. Okay, so u0 is the initial state. I take Rn u0 as the state for my semi-discrete system. All right. Now this is how would I do this null control for the semi-discrete system. Like Professor Rossi was explaining, when you null control in many techniques, the first you regularize. You let it evolve without any control input. So we do the same regularization for the semi-discrete system. Okay, we take the ODE system and don't give it any input for some interval 0 to tau. Okay, tau is less than t, and then we let it evolve, and then this is trajectory, of course, right? Vn is e power a n t Rn u0. Okay, e power a t initial state. In particular, at the time instant tau, we reach this e power a n tau Rn u0. That's our state. So what's the objective now? So we have reached this state at the time instant tau. The objective is, let me take this state at time instant tau and move it to 0 over the time instant capital tau to t. So transfer the semi-discrete system from Vn of tau to 0 in the time interval tau to t. So that's the objective here. So how do we do that? Well, let's start off with this flat output. Okay, we'll take the flat output here to be this. This is nothing but the free evolution of the semi-discrete system, the first component of that, because we know that Vn1 is the flat output for the system. So I take the same evolution of the system without any inputs. I take the first component of the flat output. And then, okay, I have this flat output, then I compute the states, I compute the input. Well, what I will see is that once I specify the flat output, it will determine the initial state, final state, and the input. The initial state, if you were to check this, because you're taken it exactly of this form and the state you're starting at is this, it turns out that the initial state determined by this flat output is Vn of tau, which is what you need. But naturally, the final state need not be 0, right? Because you did not specify anything in the flat output to make the final state 0. All right. So what we do is we use a cutoff function where you take a function psi, which is C infinity and has nice properties in terms of the derivatives, and it starts at 1, ends at 0, and all the derivatives both ends at 0. Now once you put this, now you redefine your flat output to be what you had earlier, multiplied with the cutoff function. Now you can see if you take all the yn and all its derivatives at capital T, because of the cutoff function, the final state is going to be 0. So at capital T, all the v and j's are 0 and the fn is also 0. So therefore, if you take this as your flat output, then naturally you are going to transfer from the state vn of tau to 0 over the time interval capital tau to t. Okay, so this is your flat output and this is your corresponding input. So this is the input you have to choose to do the transfer. Now, so for the null control of the semi-discrete system, it's clear. You start with 0, you take input as 0 on the time interval 0 to tau, and then on the time interval tau to capital T, you define Fn as per this expression, the way I explain how it's constructed, and that's your null control signal for the semi-discrete system. Now, what one would naturally expect for the PDE is that, okay, you would expect that suppose I take a limit of this, do I get a control signal which will solve the null control problem for the PDEs? Okay, so if you take the input to the PDE to be 0 on the interval 0 to tau, and then take the limits of the Fn's as n goes to infinity, does it converge to an F? And if it converges to an F, does that solve the null control problem? So these are two questions one has to answer. Does Fn converge to F? And does F solve the problem, null control problem? Okay, so we'll address these two questions now. So before we address this convergence of the null control signals, we need to kind of collect some results about convergence of the ODEs, right? We need to understand some results about convergence of the ODE, the semi-discrete ODEs, their solution to the solution of the PD. Okay, so this is a system PD. We have this expression Vn dot is An Vn, Bn Fn. That's your semi-discrete ODE. You want to know what about the relationship between the solution of this semi-discrete system, the relation between the solution Vn and the solution U of this system. That's what we have to establish. Okay. I already introduced the notation Rn. Rn is basically discretizing, taking a continuous function and picking out n values and getting an n vector. Sn is the opposite. You take an n vector and then get a function out. Okay, you take an n vector and get a function out. How do you do that? You basically use a step function. Okay, you get a step function so that Rn Sn is identity. Okay, so before we talk about convergence of the solution of the semi-discrete system to the solution of the ODE, of the PD, we need to kind of establish some regularity for the solution of the PD, which is what we do in this result here. So we are seeing that the solution to the PD is given by this convolution expression. Okay, what we show is that it's a unique function on the interval taking values on the interval 0 t, taking values in PC2 1. Okay, I'll explain this space in a moment, which satisfies the PD. So usually we have results for such systems. We can show results that there are solutions in just continuous functions or C1 continuous functions taking values in the domain of A, or C1 functions taking values in the state space and so on. But we need this particular space, and the reason is we are going to do finite difference approximation of the solutions. We are going to take the functions U, right, the solution U, and do a finite difference approximation. If you want that to make sense so that you can control the residue terms carefully, you need the U to be in this space. And what is this space? This is nothing but functions in H2 such that psi xx is itself piecewise differentiable. Sorry, piecewise C1, piecewise continuously differentiable. Okay, so psi xx is itself piecewise continuously differentiable. So that's what we will show. That's the regularity of this solution. The proof is straightforward. You do the transformation I mentioned earlier. You define W is U minus nu F, right? So that the control goes from the boundary to the state, all right? And then standard results will tell you that W dot is a continuous function in L2, AW is a continuous function in L2, and so on. Then you can use the expression for A2. What are the formula we have for A2 to get this result? To show that from here we can claim that the functions are actually having this, the solutions have this regularity. Okay. So now let's look at some convergence results, some properties of the semi-discrete system. Okay. So we have shown that okay, you have a nice solution for the system in this space. Now, do the solutions of the semi-discrete system converge to the solution of the PD? Okay, under what conditions? So the first result we need here is uniform in growth bound. Okay, so we have this operator an whose dimension changes, right? Whose dimension changes, and the different operator for every n. What we want to establish is the e power a and t, this matrix e power a and t has uniform bound. That is e power a and t norm is less than or equal to m e power omega t, where m and omega are independent of n. All right. So that's so here we also need a little bit more. We show that v dot. We look at this equation. V dot is a and v plus eta. Okay. And we show that the solution of this system of this equation, the L2 norm of v at t is less than or equal to m e power omega t L2 norm of v naught, the initial state. Okay, that's a uniform bound, and also there is a nice estimate for how the forcing term can be bounded. The proof of this is a Lyapunov analysis. You take the norm square v transpose v, norm square of the solution. Take the derivative, you get 2 v transpose v dot. You substitute for v dot from here to get this expression. Then an, the operator, the matrix an will contain the discrete Laplacian in some form. All right. So you use the properties of the discrete Laplacian to show that w dot is less than or equal to omega times w for some omega, and of course the forcing term. Now you get an estimate for w, and w is nothing but norm of v square, so you get an estimate for norm of v. Okay. So from here you get a uniform in n growth bound for e per n. So this is the first convergence result. So what we, the way it's stated is the way we need it. Okay. So I will, so I'll take the initial state to be u naught. U naught is the initial state, and the input is f. So initial state and input for the PDE are u naught and f, and the solution of the PDE is u. So for the semi-discrete ODE, I'll take the initial state to be r and u naught, right? The discretized version of u naught, and the input to be fn, where fn's converge to f. Okay, so we see that r and u naught, the initial state for the ODE converges to the initial state of PDE, and the input of the ODE converges to the input of the PDE. So we expect that the solution should converge, and that's what the result says. The solution of the semi-discrete ODE converges to the solution of the PDE. Okay. The idea of the proof is as follows. You take En, the error between the solution of the PDE and the ODEs, right? And then you take the derivative, you get this expression. Now here, if you look at this expression, this term is everything in terms of u. And you can use the fact that u is in PC21, that's regularity, smoothness, and then applies using Taylor series, you can show that this term goes to 0 as n goes to infinity. All right, and now this has a uniform bound. An has a uniform, e power a and t has a uniform bound. This term goes to 0 as n goes to infinity. So we can claim that en of t goes to 0. So in this proof, I have skipped a couple of things. One is I have assumed that fn is equal to f when I'm writing these expressions. But if we were to take fn, of course fn and f are not the same, then you'll get some more terms, so some more details. But the idea more or less remains the same. The other part is that the regularity result I showed you for u, it's valid on the open interval 0t. Okay, so I can't write this expression close to 0. So near 0, we have to do a different type of argument to show that en goes to 0, the error goes to 0. But away from 0, you can use this argument. All right. So this is the first convergence result. This is L2 convergence of the solution. The next one is point-wise convergence. So we put additional regularity on the input, okay, and the initial state, and then we can claim that there is point-wise convergence. The reason we are interested in point-wise convergence is, see, Vn1 is our flat output. And we are trying to, at some point, we'll see that we are taking the flat output, the limit of the flat output. We want to see if it's converging anywhere. So this is important to establish that. Okay, point-wise convergence of the flat output, Vn1 to the value of u at 0. The proof is similar. You take En to be this one, take the En dot, get this expression. You can take the derivative once more. And like in the previous case, you can use the same arguments to show En and En dot converge to 0 in the 2D norm. 2D is the discrete L2 norm. So in the 2D norm, En and En dot converge to 0. Now if En dot converges to 0, then that means A and En converges to 0. Right? So you get En and A and En both converge to 0 in the 2D norm. Now from here, we can conclude that you have point-wise convergence. If you have these two convergence, En and A and En, you get the discrete gradient of En also converges to 0. From that, you get that you have point-wise convergence. The other result we need for the semi-discrete system is uniform analyticity. So we'll show that e power a and t, right? The semi-group that's generated is analytic. Yeah, it's a matrix, but it's uniformly analytic. Meaning you can bound an to the power k e power a and t as a matrix. the norm of that is less than or equal to m to the power k factorial, m to the power k into k factorial t power k. So this m is independent of n. So that's why you have an uniform analytic estimate here. So the way the proof of this works is it's actually quite short. So you show that AN is similar to a symmetric matrix. So AN will turn out to be typically for our system tridiagonal, and there's a very standard way of showing that tridiagonal systems are similar to symmetric matrices, okay, under some mild conditions. And so we show that it's similar to a symmetric matrix, Tn inverse Sn Tn. And interestingly, the transformation, the similarity transformation you need, they are diagonal matrices. Okay, so the diagonal matrices, and there we can show that these are actually uniformly bounded in N. So the norm of these matrices Tn and Tn inverse, they are uniformly bounded in N. Okay, the eigenvalues of Sn are real, symmetric matrix, and they are also uniformly bounded in N from above because of our uniform bound on the growth of e power a n t. Okay, so the eigenvalues of Sn are also uniformly bounded from above. So in other words, what we have is this matrix we are looking at, a n to the power k e power a n t, is nothing but it's a matrix similar to diagonal matrix whose entries are of this type, lambda I power k e power lambda I t, where lambda I has an upper bound which is independent of n. So these entries satisfy an estimate like this, so we can clearly see that this matrix also satisfies an estimate like this. All right. Okay, so now so far we have seen that with some properties of the semi-discrete system, what we want to show is this null control signal that we created for the semi-discrete ODE. We want to show that this converges as n goes to infinity. Okay, here yn is the flat output which I defined earlier, is given by this expression. So the questions again are, does fn converge to a limit f, and does the limit f solve the null control problem? Okay, so now if you look at fn, it has two components. One is these coefficients which depend on n, and then there is this function yn which also depends on n. So we have to show that both these coefficients converge as n goes to infinity, and then we also have to show this yns converge as n goes to infinity. If they both converge and in some nice way, then we can say that fn converges to f. So next first I'll focus on the convergence of the coefficients as n goes to infinity. Okay, because I'm focusing on only the coefficients here, I'll just take y to be a constant. Instead of yn, I'll just put a y. Okay, and this y will assume it's a function in it's a Gavrier function of order alpha, which means that the function's derivatives, the kth derivative of the function, is roughly bounded by k factorial power alpha. And alpha, we have to take it between 1 and 2. We'll see in a moment why that's the case. Okay, so we take a function in of this type, a Gavrier function of order alpha, and then we have this expression for the series for the states, and we have the series for the input. So typically, how do we find these coefficients? Okay, so the way we find it is we look at this expression. We have this expression where Vnj plus 1 depends on Vnj and Vnj minus 1. So we know Vn1 is nothing but the flat output. Therefore, Vn1 is the coefficient for Vn1 is 1. Okay, for Vn2, I'll put it into this expression, and then I'll find the coefficients for Vn2. Similarly, I'll put so because I'll know the values for 1 and 2, I'll find the value for 3 and so on. So this is a recursion in J, right? So if you are taking an example, right, fourth order, if you take n is equal to 4, a semi-discretization of fourth order system, then I'll find d1 0, d1 0 will be 1. Okay, then I'll use that formula to get d2 0, d2 1, and then d3 0, d3 1, d3 2, and so on. This is how we proceed. Okay, now there's another way of getting these coefficients, which is doing it column wise. Okay, so if I can do it column wise, then I'll be able to get a recursive expression, a discrete time system which I can solve. Okay, I'll explain how I get it column wise. So I have this expression here. I can substitute these formulas. Okay, if I do that, I get an expression of this type, where dj plus 1k, where I basically compared the y to the kth derivatives of y on both sides here. I substitute the series for Vnj plus 1, Vnj and Vnj minus 1. Then compare the coefficients of y to the power k, the kth derivative of y, right? And I get this expression. So here, if I know everything at k minus 1, that is the previous column, I can try to compute things at the current column. Okay, so I can show this here in this table. Suppose I know everything at k equal to 0 and k equal to 1. Then I can compute D32 using the two numbers above it and the number here, D21. Can compute D42 using the two numbers above it and D31. And then I can compute D52 using the two numbers above it and D41. Okay, so I basically have to solve this discrete time system. So if you think of this as a discrete time system, basically the discrete time system is evolving along this column, and the forcing term is coming from the previous column. Okay, so I can write it as a discrete time system. So this is for j plus 1. So the column is k, I fix the column k. So this is a discrete time system, it's evolving. Okay, the current values depend on the previous values, and the forcing is coming from the previous column, k minus 1. Now if I have this, using the properties of this matrix, looking at its eigenvalues, I can compute a solution to this equation, or estimate the solution to this equation. So suppose in the k minus 1th column I have these estimates. Okay, that k minus 1th column, the coefficients are bounded by r naught to the power k minus 1, j to the power 2k minus 2 by 2k minus 2 factorial. Suppose I have this, I put this in, then I get a convolution expression for this discrete time system. Estimating the eigenvalues of this guy, I can kind of compute the estimate to be this. In other words, by induction, I can show that the coefficients on the kth column satisfy this estimate. Okay, r naught to the power k by j into j to the power 2k by 2k factorial. Now, when I have all the coefficients for the Vn's, I can compute the coefficients for Fn. Because the coefficients for Fn, they depend on the coefficients dn k, dn minus k, and so on in this example. Okay, so I have these estimates. Using these estimates, I get this estimate. These estimates for the coefficients for Fn. These are the estimates I have. Okay, so now suppose I denote this dn plus 1 comma k into h power 2k. This whole thing as a and k. So this is the expression for Fn. And what we have shown is this a and k's have this satisfy this bound, r power k by 2k minus 2 factorial. All right. Now, for every k, this is an as n goes to infinity, right? This is a bounded sequence, right? And you can show that in fact it's naturally it has a converging subsequence, but in fact you can show it's a converging subsequence. You can show that limit n going to infinity a and k is in fact some constant a k. All right. So you have shown that the coefficients here, these coefficients in fact converge. So the coefficients converge a k. Now when you have y, which is a Gavriado alpha, then you can also show the functions converge. The reason is, okay, when you look at this summation here, okay, so these coefficients are behaving like 1 by 2k minus 2 factorial, and y to the power, the kth derivative of y has an estimate something like k factorial per alpha, where alpha is between 1 and 2. Okay, so therefore if you take this product, then of course it's going to be something small as k increases. Okay, so therefore the convergence for any y in G alpha is not difficult. Once you have these estimates for a and k, and you know that the whole series converges. Okay, so this is basically showing the convergence of the coefficients. We still need to work out the convergence of yn, because the null control input, okay, is basically this coefficients and the yn. Okay. So yns are given by this expression here. We need to show this yns also converge as n goes to infinity. So what we'll show, okay, in the next slide I'll explain how this works out, is that this function basically converges to, the natural guess is this, a n power k, you guess it will converge to the operator a to the power k, and e power a and t, you guess it will converge to the semi-group tt. That's your guess, so this is at the first component, so you expect this to be at 0. Okay, this is a natural guess, and this is what works out. Okay, so yn, the limit of yn, and this convergence is in any ck norm. So the limit of yn is basically y, which is given by this expression. So the yns converge to y in any ck norm to this expression y. So how does the proof work? So what we do is we take the difference of these two things. We want to show the difference is 0, right? So we take the difference as error, right? R and ak tt minus a n or k e per a n t, the two things that we want to compare. Initially, I assume that the initial state is very smooth, so u infinity. What I want to show is that this converges in 2D norm. First, I'll show that it's converging in 2D norm for all such u infinity functions. The limit, now this limit holds for k equal to 0. That's easy to see. If you put k equal to 0, you're simply comparing the solution of the PDE and the solution of the semi-discrete ODE. which we know that by convergence that they actually go to, the difference goes to 0. So when k equal to 0, the convergence is clear. Now En k plus 1 can be written in this form where you have in terms of En k, okay, and this term. Now this term, if you see again, because U infinity is smooth, using Taylor series, you can say that this thing goes to 0 as n goes to infinity. And this object, this matrix, this operator here is uniformly bounded because we had uniform analyticity for this e power a n t, right? Therefore, this is uniformly bounded. This is going to 0 as n tends to infinity. Naturally, this term goes to 0. All right. Now, if you assume that for the kth, for E and k, this expression holds, then naturally from this you get it holds for E and k plus 1. So by induction, you know that it holds for every k. So this is true for when the initial state is smooth. When the initial state is not smooth, you use a density argument and then you get the similar result. The next thing you do is you do this for E and k, then you write E and k plus 1 in terms of A and E and k. And like we did in the corollary earlier for getting point-wise convergence, we will show there's a limit for E and k and A and E and k. So if you have these two in 2D norm, the convergence of these two in 2D norm implies point-wise convergence, and therefore you get the result. Okay, so the input to the semi-discrete system is this. We have shown that the coefficients converge, right, and they have a nice bound. And the flat output for the semi-discrete systems yns, they also converge, and they satisfy. They also have this. So we have not. I'm not sure discussed it here, but y will also be a Gavre function of order alpha, because all the yns are Gavre functions of order alpha. And because we have this convergence of the coefficients and the convergence of the yns, we can conclude that the inputs also converge. Now the question is, does f solve the null control problem? Because we have shown the convergence, does f solve the null control problem? Well, the state of the semi-discrete, so what we do is we let both the semi-discrete system and the PDE to have 0 input for the first tau seconds, okay? So the state of the semi-discrete system at time tau is this, free evolution. And the state of the PDE at time tau is this, again free evolution. And easy to see that these two initial states, right, the initial state for the semi-discrete system and the PDE system at time tau, this difference goes to 0. This comes again from our convergence result. Now the input to the semi-discrete system is Fn, and it converges the input F to the PDE system on the interval tau comma t. This is what we have seen just now. So the initial states converge, the inputs converge, so we can conclude that the states of the semi-discrete system will also converge the state of the PDE. Okay, so the states of the semi-discrete solution of the semi-discrete system will converge the solution of the PDE. Now this Fn that we have, for this initial state, this Fn ensures that the state of the semi-discrete system is 0 at capital T. That's because Fn is a null control signal for the ODEs. So therefore we can conclude that because Vn of t is 0 for all n, we can conclude U of t, the solution to which Vn's converge, is also 0. Or the solution of the PD at capital T is also 0. Okay, so this is quick summary of how the approach works. You take the parabolic PD, okay, what is given. You do semi-discretization, you get a semi-discrete ODE. You fix any tau on the interval 0t and let the semi-discrete system evolve, okay, with no input. Then it reaches some state Vn of tau, which is e power a n tau Rn u naught. Now once it reaches this state, you choose an Fn, smooth function, which transfers via flatness, like I have explained before. You just choose an Fn which transfers Vn of tau to Vn of t equal to 0. You do this via flatness for the semi-discrete system. Now for n large, if you take this 0 signal concatenated with this Fn, right, this is a good approximation of the null control input for the PD. And if you take n to going to infinity, you in fact get a control signal which solves the current control problem for the PD. Okay, so I'll conclude with an example. So I have this parabolic PDE here. I've taken the coefficients as shown here. Theta is a step. Okay, it's a step at 0.5. Sigma is also discontinuous. It's also spatially varying. This is piecewise constant. This is piecewise continuous. Piecewise C1. And lambda has discontinuous at both at 0.5 and 0.3. And I take the initial state to be discontinuous function. It is 0 on some interval, and in between it is -1. So it's something, it's 0 on these two intervals, and in between 0.3 and 0.7, it's a step, -1. So I construct the control input using semi-discretization. So I take n is equal to 5, n is equal to 20, 50, and I plotted for this. So for the simulations, I have to let take some time in which it regularizes. So I've taken that time to be 0.05 seconds. The full time interval is 0.5 seconds. So the null control problem has to be solved in 0.5 seconds. And the regularization is happening in 0.05 seconds. Okay, so this is so the input is 0 here, Fn is 0. Then I construct Fn starting from here using the flatness approach. Now, as you can see, beyond n is equal to 20 or so, there is not much difference in the picture numerically between the Fn's once you cross 20 or 30. So if you were to take, say, Fn, F50, so if you do a discretize system, if you discretize your heat equation with, say, 100 nodes, you have more or less a very good approximation of the null control signal. So in this plot, what I have done is I have taken the input F to be F100. So the null control signal I obtained by discretizing using 100 nodes. Okay, and you can clearly see, so you have the step input, discontinuous input here, and within 0.5 seconds you do have convergence to the 0. Okay. So with this I will conclude my talk. Thank you for your attention.
Thanks, Vivek. Well, I have a question on the, when you use this cutoff function to bring the solution to 0, can you use other trajectories going to other states?
So I didn't get the last part. I use the cutoff function to go to 0, yes?
Yeah, so can you use or build other trajectories going to other states?
Yes, yes. So in fact, the way we have done it is we have tried to understand what type of motion paralleling problems can you solve. So what type of initial states and what type of final states can you take? So in fact, I have presented in this talk just a null control problem going to 0, but in general, we are looking at, within the context of this approach, what are the possible initial conditions and what are the possible final conditions. And I think recalling from Professor Rosier's talk, we can handle some polynomials in this technique, but not all, but some polynomial states can be reached.
And if you try to go to a state where you know that you cannot going with the heat equation, so there are some problem with the...
Yeah, but because in the hypothesis of where you can go, right, it will automatically appear. So you cannot, so we have some conditions on what the initial state and final state should satisfy, okay? And there are some stringent estimates. If they satisfy that, then you can go between them. So that includes some polynomials.
But I suppose that convergence part is failing, no? The convergence part.
If you want to go to a state which you know is not reachable, then yes, it won't work.
Yeah, because at the discrete level, you can find a control, no? But the convergence thing, I think that it fails.
At the discrete level, you find the control, but when you try to do this type of a thing and take it forward, it will not work. Right? You have a discrete null control signal, but we'll not be able to, discrete control signal for the motion planning. But when we take the limit, we'll not be able to show that there's a limit if the point is not reachable.
Thanks, Vivek, again for the nice talk.
Thank you.